So it's time. I will just introduce you and then you can take over. So good afternoon, good morning, good evening, everybody. It really gives me great pleasure to welcome Zoltán Fodor to give the 12th OSMU lecture on the magnetic moment of the muon. Zoltán is a professor in the physics department of the Eberly School of Science at Penn State University. And as you can see from his opening slide, he has several other affiliations too. Zoltán's research interests are in particle physics theory and phenomenology. He received his PhD from the Eötvös Loránd University in Budapest. His early career included several years of research at CERN, DAISY, Keck, and the Eötvös Loránd University. In 1998, he became a professor at this university in Budapest, and in 2003, he moved to the University of Wuppertal. In 2020, he joined Penn State, and since 2005, he has also been the spokesperson of the well-known BMW collaboration on the hadronic contribution to the muon's magnetic moment. Zoltán is a fellow of the European Physical Society and an honorary member of the Hungarian Academy of Sciences. In 2010, he received the Top 10 Breakthroughs of the Year award for determining the hadron spectrum. The highlights of Zoltán's work include ab initio determination of light hadron masses, a full result of the QCD equation of state with 2+1 flavors, ab initio calculation of the neutron-proton mass difference, and the celebrated calculation of the hadron vacuum polarization contribution to the muon's magnetic moment, which is what we hear about today. And it's really a pleasure to have you with us. Over to you, Zoltán.
Thank you very much for this very kind introduction. And as you mentioned, I'm going to speak about the magnetic moment of the muon. I have to apologize. I got a cold, so I hope I will go through the whole lecture. But if my voice is getting weaker, you know the reason for that. So the topic of the magnetic moment of the muon is something, a hot topic, and my main focus will be a paper of 2021 and a very recent preprint on the archive. These papers were written within the Budapest-Marseille-Wuppertal collaboration. Some people call us BMW. So if you see these three letters, then don't mix it with a car company. It is just the name of the collaboration. So that's the good news. The bad news is that these two papers are lattice QCD papers. And I don't know if you have heard recently lattice talks, they can be terribly boring. But I will try to do my best and avoid all those technicalities which make the lattice talks boring, and I will concentrate on the physical inputs and the physical outcomes. So that's somehow the interesting start about 3 years ago when Fermilab published their result on the magnetic moment of the muon, a beautiful experiment, and on the same day, Nature published our lattice QCD calculation. And it was everywhere in the press, from the Frankfurter Allgemeine Zeitung to Forbes magazine, from Wall Street Journal to Le Monde, from Yahoo to the New York Times, which kept the story 2 weeks long on their opening webpage, which is not so common for a scientific result. And at the end of the year, 2021, this result became one of the breakthroughs of the year. And the text said that on the same day, experimenters released their result. One team of theorists published a calculation that they argued increase the standard model prediction and closes the observed gap. So I'm coming to speak, I will speak about this observed gap and how we closed this gap. Let me mention that the breakthroughs of the year as usually 10 scientific results in all science. So most of them are in biology, and typically 2 of them are in physics. So that was one of the physics results. By the way, you can stop me anytime. We can have a discussion on some points. I don't mind that. So let me start with the take-home message of that time of 2021. And here what you see is the 9th, 10th, and 11th digit of the magnetic moment of the muon, actually the half of it. 20 years ago, the Brookhaven experiment measured the magnetic moment of the muon with a quite beautiful precision, and that's what you see here as a green dot. Fermilab, 20 years later in 2021, had a similarly accurate result, even somewhat better. And if you made a experimental average out of that, you obtained what is shown here by the green band. That experimental average was in strong contradiction with the so-called white paper result. The white paper result was written by 134 physicists. They wanted to have 137. They couldn't manage it, but it's still a huge number of physicists. And the result was based on the so-called dispersion relation method, or on the R ratio method, or the data-driven method, or they even called themselves a theory consensus value. I don't like that name, theory consensus, because science is not a democratic institution, so it's not the majority or even a consensus decides what is true or what is not. Anyhow, as you see, there was a 4.2 sigma discrepancy, and the journalist thought that this is essentially a 5 sigma, so we can celebrate the discovery of a new interaction, a new force, you name it. At the same day, as I said, on the same day, the BMW collaboration published their result, and that is shown in this pink band. As you see, there is no strong discrepancy. The BMW result agrees on the 1.5 sigma level with the experimental average. It even has an overlap with the Fermilab result. As we all know, 4.2 sigma is not enough. We have an arbitrarily defined 5 sigma where we say that something new happened, but that means that one has to improve on the accuracy of the experiment, and you have to improve on the accuracy of the theory, because this is a theory calculation, this is another theory calculation. And that's why Ed Witten, very shortly after this paper, said that the dream would be to get a concrete clue about what is the energy scale for new physics, and it is very important to improve the lattice gauge theory estimates of the hadronic contribution to the muon. And that's somehow the passage, what I'm going to speak about here, how the theory predictions is getting better and better.
Sorry to interrupt you. This remark by Ed Witten is after your paper.
That's correct.
What does he mean by improve the lattice? It's already there, no?
Yeah, the accuracy, I think the accuracy should be improved. That's what he meant.
Mhm. But could that produce a 5 sigma discrepancy?
One day, most probably. But as we see on the next slide, it is not the day of today.
Okay,
So
okay.
both the experiment reduced the error by about a factor of 2, and the BMW also reduced the error by almost a factor of 2, and they shifted even a little bit closer to each other. So that's the take-home message from 2023-24.
Hmm.
As you see, the green band, first we look at the upper part of this plot. The green band is thinner. The pink band is also thinner. They shifted a little bit closer to each other. So the 1.5 sigma became 0.9 sigma.
Hmm.
And you see how the magnetic moment measurement from Brookhaven just moved and became more and more accurate. What you see here also, that the BMW, which is a theory result, disagree with the white paper on the 4.0 sigma level. And even more surprisingly, the experimental value of the magnetic moment, which is the green band, has a tension with the white paper on the 5.2 sigma level. So it is now beyond the 5 sigma level. Nevertheless, nobody is speaking about the discovery of the century anymore. And that is basically because of the lattice result, which created some bad feeling about the white paper procedure, and a CMD3 result, which is an experimental result, which is going into this R ratio or dispersion relation technique, which I will discuss soon, and which is also much higher than the white paper result. It agrees with both with the lattice calculation and with the direct experimental measurement of the
Could I
muon.
ask you something, Zoltán?
Sure,
Before,
absolutely.
before your paper, the white paper authors, what was their take on the lattice QCD distribution?
So the white paper, if I remember correctly, the white paper was written after the BMW 20 result. So here is the BMW 20 result, yeah?
Mhm. Mhm.
And the white paper was written later, but they didn't take it seriously, the lattice result.
Okay.
And, the criticism was that one result is no result, we shouldn't trust, and there was, in my eyes, a sort of wishful thinking that we will have a 5.2 sigma, and that will be a discovery of a new force, a new interaction.
Mhm. Thank you. Thank you.
But this is just my personal feeling. Yeah? What I'm saying that in the white paper result, the BMW result was not included.
Okay. Okay.
Yeah. And if you look at the paper of the Fermilab experimental group, then you see everything from this plot except the lattice result. So they knew the lattice result, they got it, but they didn't take it very seriously. They were focusing on this 4.2 sigma discrepancy between the theory delivered by the white paper and the experimental result.
Mhm.
So good. So far, so good. So you see that the experimental average is more and more precise. The lattice average is also more and more precise. Unfortunately, the situation hasn't changed. So in 2020, there was only one lattice result, which had a comparable error to the white paper. And today there is only the BMW which has a comparable error, the BMW 20 and the BMW 24. No other collaboration came out with a full result. And one result is no result, so I'm eagerly waiting for other collaborations, either to confirm or to refute our result. So good. You might think that lattice QCD, which was somehow a toy model, a game for a long, long time, is not a serious player here when we want to reach an accuracy which is really incredible. But let me convince you that it is not true any longer and show you 4 results of our collaborations which you cannot get by any other means. One of them is the order of the quantum chromodynamics transition. That is the transition in heavy ion collision and perhaps even more importantly in the early universe. And it was believed to be a it was believed to be a first order phase transition for a very long time, but we showed that it is not a first order phase transition, it is actually an analytic transition. There is no singularity in a finite volume analysis, which showed that it is not like melting ice into water, but it is much more like melting butter with a continuous transition. Another result was the ab initio determination of the light hadron masses, against something you cannot get by any other means. And here is the spectrum, a hadron spectrum for about a dozen particles. And as you see, it is in complete agreement with the experiment. Here, the experimental value of a hadron mass is shown by a horizontal line, and the width of that particle is shown by the gray band. So the rho has a relatively large width, or the delta has a relatively large width. The input, which in principle define the light quark masses, are pi, and the strange quark mass is k, and the QCD results are shown by these red points. And as you see, there is a beautiful agreement everywhere. A few years later, 7 years later, we were able to determine the isospin splitting of the hadron multiplets, most importantly, the splitting between the proton and the neutron. And as you see here, the scale was 1,000, 2,000 MeV, and here the scale is a few MeV. So it's an incredible improvement in the precision as time passed. Let me emphasize here that some of the results are agreement with the experimental result, but the blue shaded results are either better than the experimental result, or there is no experimental result at all. So these are not postdictions like the mass of the nucleon or the omega, but here about half of the results are predictions. And my final example is the lattice QCD for cosmology. And here you see the equation of state of the early universe for a huge temperature range. And that's again something you can get only by using lattice field theory. So that brings me to the G-2 topic. And let me show you a sort of outline in which I tell you the inputs in the various techniques here in this page. So the experiment uses the input of the Brookhaven and the Fermilab experiments, and they are in complete agreement. We have to remember that the total error is statistics dominated, which is always good because we cannot control the systematic errors as precisely as we can control the systematic errors. And if the total error is dominated by statistics, we can control; systematics, we cannot. So if the total error is statistics dominated, that's a good news. And the final error of the Fermilab result will be even smaller than I showed you, because they have a lot of data on tape and they will analyze it. Let me move on to the so-called data-driven method. That was the white paper result, or the blue band. The input in this technique is the hadronic A plus C minus R ratio. And I will discuss this R ratio in a bit more detail, but that means that you need thousands of data points. So I've also carried out this calculation, the white paper calculation, and there I have used 4,549 data points for the E plus C minus collision, hadronic collision. And one important feature of this calculation, that it is systematics dominated. It's not so easy to figure it out, but if you go to the Davier paper, you can see that the systematic uncertainties are about 4 times larger than the statistical ones. And it's never good to have large systematic uncertainties. Then I finally discussed the lattice technique. And here the input is nothing else but just the Lagrangian with the 4 quark masses and the fine structure constant. The 4 quark masses are hard to calculate, and then we use just proxies for these 4 quark masses, the pion, kaon, omega, and ds. In this calculation, the systematic uncertainties are about the same as the statistical ones. They are well-balanced, far more well-balanced than in the data-driven method. So this is the outline in which I also listed the inputs in the various bands of my take-home message figure. And that brings me to the experiment first. I'm not an experimentalist, but for those who perhaps need a little bit of the refreshing how it is measured, let me say a few words. So we are speaking about the muon. It was discovered in 1936 in cosmic rays. It's about 200 times heavier than the electron, but the charge and the spin are the same. It has a short flight time of 2.2 microseconds. It will play an important role, the decay of the muon, and obviously acts like a tiny magnet. Here is the magnetic moment with the G factor. In Dirac quantum mechanics, G is 2, but we will have corrections, and it's 2.00233, and so on and so forth. People are usually using A mu, which is G minus 2 divided by 2. So we subtract this 2 and divide the rest by a factor of 2. So what are the experimental results right now? The newly announced results at Fermilab is shown here. Of course, you don't need to remember this number. The only thing I'm pointing out is the error. So I will give everything in units of 10 to the minus 10 in the rest of my talk. And the error in these units, in the units of 10 to the minus 10, is 2.4. So please remember this number, 2.4. And that's a very small number. It's like having a bathroom scale and having it be sensitive to the weight of a single eyelash. It fully agrees with the BNL experiment. As you see, the BNL experiment had almost a factor of 3 larger error. And the combined number has an error of 2.2. So slightly reduced the Fermilab result to 2.2. Before I move on, let me emphasize that the target uncertainty will be about 1.6. Actually, I think that they will be even better than that. And in the meantime, there is a Japanese experiment, and this Japanese experiment will have a similar accuracy, and they will start in 2024, 25, 26. It's not clear when they can start. So these are the experimental results, and let me remind you how it was measured in time. So the first measurements were around 1957, and that was a 10% error on GMA, but the accuracy was getting better and better all the time. And as you see, it was 220,000 in these units, then 3,000, 110, and so on and so forth, all the way down to Fermilab, which has an error of 2.4 right now. The problem with Brookhaven was that they had a very large and very expensive magnet of $30 million, but they didn't have enough muons. Fermilab had the most intense beam of muons in the world, so the idea was to bring these 14-meter diameter magnet ring to Fermilab. And you probably all know that they put it onto a boat, then sailed down on the west coast, on the east coast of the US. Then they were sailing around Florida all the way to the Mississippi. Then they went up on the Mississippi, and then the magnet was transferred to Fermilab. And then Fermilab, with their intense muon source, were able to measure the magnetic moment even more precisely. So what is the principle of the measurement? The muon is an electrically charged particle. That means it is moving around in a cyclotron way in a magnetic field, and this is the cyclotron motion frequency. At the same time, the muon is also it also has a spin and a magnetic moment, and this magnetic moment is also precessing around the magnetic field. And the spin precession frequency is almost the same, yeah? And the difference between them, between the cyclotron and the spin precession frequency, is proportional to a mu. And that's a good thing, because what you do, you put your muon into this magnetic field, and you look how much faster it is, the spin's precession frequency, than the cyclotron frequency. And if you measure the difference between them, then you essentially measured a mu. So this is an illustration. What's happening? A muon is coming in, and the blue arrow shows the momentum of the muon. So the muon is flying around in the magnetic field, but the spin precession frequency is slightly larger. So when it moves a little bit further away, then the spin shows a little bit in the clockwise direction. When you look at even further, then it is more and more and more and more deviating from the direction of the velocity. Actually, during each circle, the spin axis changes about 12 minutes. How can we use that to measure the magnetic moment? So first of all, the first step is that pions are produced at fixed target. Then these pions decay through weak interaction, producing highly polarized muons. Here we have these mu plus. And the muons decay after several circles. That means we will detect high energy positrons in our detectors. And there is a strong correlation between the spin of the muon and the positron's momentum. That means that when we detect the emitted positrons, then we will see an oscillating structure. When the spin points to the direction of the detector, then we have a lot of electrons. When it points to the opposite direction, then we have far less positrons. And this oscillating function has a decaying feature, obviously, because we have less and less muons in the ring, but the oscillation frequency is telling me how much faster the precession is going on compared to the cyclotron frequency. And how much faster it is actually a measure for AMU. So that's the basic idea behind the measurement of the magnetic moment.
Sorry, could I interrupt you?
Sure.
If AMU is 0, what would this figure look like?
If AMU were 0, then it would always show or would point in the direction of the velocity.
Right.
So there won't be any oscillation.
So the figure in your next graph would just show straight lines, is it?
Straight decaying lines. So
Straight decaying lines, yes.
This is an exponential plot,
Yeah.
and it would be a straight
linear as opposed to oscillating. Thank you.
Yeah. And the larger the difference between the cyclotron motion frequency and the precession frequency, the more rapid will be these oscillating feature. And if the difference is 0, then it's getting smaller and smaller, this frequency between them. And as a final hypothetical case, when there is no difference between them, then there is no oscillation at all. But nature is as it is, so we will certainly have that. And that's not just an experimental fact, but it is also calculated in theory. And the first calculation was done by Julian Schwinger, who calculated this first contribution to the magnetic moment as alpha over 2 pi. And he was so proud of that actually on his gravestone, you find this alpha over 2 pi. He was, as you all know, he was an excellent teacher, so not just an excellent scientist, but an excellent teacher. He had 4 students who also got the Nobel Prize. And the only person I know who had 4 students in Nobel Prize was Sommerfeld. He also had 4 students with Nobel Prize. The sad part of the story that he never got it, in contrast to Schwinger. After this side remark, let me show you that the magnetic moment of the electron or muon is a great success of the QED perturbative approach. Why is that? So here you have the fine structure constant, which is small, and that means that there is a way to calculate very precisely the magnetic moment of the electron. And here are the necessary graphs. Electron is coming in, going out, interacting with the magnetic field, or coming in, emitting a photon, absorbing it, or emitting a photon, which produces an electron-positron pair, which annihilates, and then it is absorbed. And if you calculate many more graphs, you will have a 14-digit agreement with the experiment, but that's mostly the electromagnetic contribution. So here is the experimental value of the magnetic moment of the electron, and here is the theory value of the magnetic moment of the electron. So for us, this contribution will play an important role for the muon, and the reason is twofold. The muon is heavier, so it can somehow feel other vacuum polarization graphs, so this sort of graph we call vacuum polarization, namely when we have hadrons here. The problem is that the coupling is not 1/137, but it is around 1. So no perturbative method can work there. And that will be the main topic of the present talk, how to calculate these vacuum polarization term for the muon, including hadronic particles. So we have the standard model, and we have these virtual particle contributions. We have the QED with photons, leptons, electrons, muons, whatever. Then we have the weak interaction, where we have in this bubble not the electrons or positrons, but we can have W plus W minus bosons, which are heavy. So we have W, Z, neutrinos, Higgs. And finally, we have the strong interaction where we have quarks and gluons. And it's obvious what is the strongest contribution. This is the QED, because the electron has a very small mass. The second largest contribution is the strong interaction, because the lightest hadrons are much lighter than the weak bosons, and the smallest contribution comes from the electroweak theory. So here is this white paper list of the literature. So this is the QED contribution, what you see here. And on this level, to the 10 to the minus 10 level, the error is 0. The electroweak contribution is tiny, with also a negligibly small error. You remember the experiment had an error here, 2.2. And the QCD contribution, which is between the QED and the weak theory, 693, with an error of 4.3. So all the error is coming from the QCD contribution. The QCD has a 4.3 error. And actually, the dominant QCD error is the vacuum polarization, which I showed you on the previous slide. So the vacuum polarization in the white paper is 4.0, the error. And in the BMW 24 result, it is 3.3. So
sorry, I'm a little confused. Earlier, you said that the white paper did not take into account the QCD contribution. That's what I understood. But
the white paper didn't include the QCD lattice result,
which gives a different number from 693.7.
Yes. So it is not the 693. And that's why in these results, let me come back here. Here, you see a discrepancy between the lattice-based calculation of the magnetic moment and the white paper calculation.
And so you have probably some criticism of the white paper's QCD calculation. You are suggesting, to my understanding, that that calculation is less accurate and credible compared to the lattice calculation.
That it is less accurate is obvious because their calculation has an error of 4.0. Our calculation today is 3.3. The question is, the tricky part of your question is whether it's trustworthy or less trustworthy. And what I show you here already in this plot, that the white paper, which used Chloe and Babar, mostly these two experiments, to calculate the hadronic contribution to the vacuum polarization. These two experiments are in strong contradiction with the most recent experiment, CMD3. So these are E plus E minus going to hadron experiments. They dominated the white paper result.
Okay.
But the new result, the CMD3,
Okay.
is in contradiction with Chloe.
Okay. Okay. Thank you.
Then you can decide whether you trust these results or not, if there is a strong contradiction within the calculation.
Okay.
Did I answer your question?
Yeah. So maybe the white paper people and the Fermilab people would come back and say, oh, maybe we believe the white paper QCD contribution more, or they agree that your lattice calculation is the one to be trusted more than the white paper's QCD calculation.
I mean, I'm not part of these 134 people. I'm not part of the white paper. And I can imagine that it's a very hard job now. Yeah, because they have the lattice result. They always criticize the lattice result that there is only one single lattice result. Yeah, that's true. The BMW is the only lattice result, but hopefully other groups will come out soon.
Okay. Yes. Thank you. Please go ahead. Please go ahead.
Okay.
Yeah.
So we were here. As you see, the error comes from QCD, and the dominant error in QCD is the vacuum polarization. So the graph which we discussed just on the previous slide. And this vacuum polarization error in the white paper is 4.0, and in the BMW 24, it's 3.3. And you remember the Fermilab result had an error of 2.4. Yeah? So still better than the theory error. So far, so good. So how does the white paper determine the vacuum polarization contribution? So they were using the so-called R ratio. That means E plus E minus, annihilation goes to photons, photons go to hadrons, and they normalize it by the hadronic cross-section. Then they normalize the hadronic cross-section by the mu plus mu minus cross-section. And here is the theoretical procedure. There is the so-called optical theorem, which is correct. So it's a 100% correct theorem. And that means that this vacuum polarization contribution is related to the total hadronic cross-section. Gamma goes to all possible hadrons, can be related to this vacuum polarization. And this graph, gamma goes to hadrons, is the so-called R ratio, and you can find this figure in the particle data group. So here you have various resonances, and here you have the thousands and thousands of measurements of the E plus E minus hadronic annihilation. And there are 60 years of experiments on that: CMD, SND, BES, Chloe, Babar, you name it. And the only thing you have to do, you take this R ratio, here it is, you multiply it with a kernel function, which is analytically known, and integrate it. And that gives you the contribution through the vacuum polarization hadronic channel. So that's all, that's what people calculated. It's not a very complicated calculation. As I said, I've done it on my own. Of course, the most difficult part is to collect these data, these 4,500 something data points, and the correlation between them. Anyhow, the white paper result is 693 with an error of 4, as we already discussed. And that brings me to the main topic of my talk, is to lattice field theory. So this is a systematic non-perturbative approach. In a way, it's a numerical solution of the quantum field theory. Where we use the path integral formulation. That means we calculate the action, similarly as we calculate the action in quantum mechanics. And in quantum mechanics, we use these action for all possible classical paths, and then we add these phase factors x, I, s, and that gives us the transition amplitude. In quantum field theory, we do exactly the same. We calculate the action for all possible classical field configuration, and we add them up as a phase factor. Of course, this phase factor is a strongly oscillating function, and that's why people are usually working in Euclidean spacetime when xis becomes exp minus s, which is just the sum of some Boltzmann factors. And then we numerically evaluate this sum. We use a spacetime grid for that, which means that formally we have a four-dimensional statistical system, and we extrapolate to the continuum limit, which a goes to 0. So this is a stochastic approach, and it's easier said than done, but with reasonable spacing and reasonable size of the system, it is solvable. So there is a deep theory algorithm CPU part of those projects. And the bad news is that you can make your projects cost 1,000 times more than by using another choice. So it's very easy to make it very expensive, and it's very hard to get the most physics out of your available resources. So how does it work? So we need a fine lattice to resolve the structure of the proton, which means the lattice spacing must be smaller than 0.1 Fermi. And you need a few Fermi size of your system. That means you need 100 to 200 points in all directions. But it does make a difference whether you use 100 or 200, because it means about 100 to 200 times more CPU. At the end of the day, you need supercomputers, because this is mathematically a 10 to the 11 dimensional integral, which cannot be carried out analytically. So the technique is called importance sampling, which you all teach in fourth semester or so. And we have very advanced techniques, and a good balance is needed between the ingredients in petaflops, 10 to the 15 floating point operation per second, needed 24/7. Once you have done it, you will have typical field configurations in your quantum field theory. And a typical field configuration would look like something like that. And here it is. This is a visualization done by the University of Adelaide, Australia, and it very nicely shows you the action density as a function of space and time. So far, so good. So once you have these typical configurations, then you can calculate the current correlator on these configurations. Because this graph, what we were looking at, it was an electromagnetic current here and an electromagnetic current there. So once you have the electromagnetic current correlator, then you can calculate the contribution to the magnetic moment of the muon. The contribution based on the hadronic vacuum polarization. And here is this correlation. You multiply it with some kernel function. This kernel function is also known analytically. And after you integrated it, you have the magnetic moment contribution from this current correlator. And here I show you this integrand as a function of t in our 2017 and in 2020 calculation. And as you see, the error of these calculation was reduced dramatically. So in 2017, we had these red points with larger error bars, and in 2020, we had the blue points with much smaller error bars. That was called, it was used a technique which we call the wall-to-wall propagator, but these are some details which I don't want to speak or spend too much time on it. But this one example already shows that a reduction of the error and the reduction of the most important error is somehow plays the most important role in this calculation. And to tell you how it happened, I'm showing you the error reduction from 2017 over 2020 to 2024. There are a few sources of errors. Here I show you the statistical, the finite size, the continuum extrapolation error, the physical point error. That means that we have to tune our system to the physical values of the pion and kaon masses. And these are spin breaking errors because we have different quark masses and different charges. And as you see, the blue columns are the 2017 results, and the largest error was coming from the finite size. And then we reduced it tremendously, and that's what you see by the green columns, which are the result in 2020. And the reason for that reduction was that earlier we used only 6 Fermi boxes and we increased it to 11 Fermi. As you see, we further reduced this error in 2024 because we separated the tail. And I will show you soon how we did that. In 2020, when the green was the result, you see that the largest error came from the continuum limit extrapolation. So we introduced a new, even finer lattice, which took us closer to the continuum limit. And that lattice spacing was 0.048 Fermi. And in that way, we had altogether 7 lattice spacings. And as you see, we were able to reduce the error to 0.27%. The statistics and noise was also reduced by these so-called all-to-all propagators. But let me emphasize that most of the noise comes from the tail, which was at T larger than 3 Fermi, and I will come back to the tail calculation using a data-driven method. Anyhow, the scale for physical point and for the isospin breaking analysis remained the same. As you see, they were already very precise and they had only a small error. So the situation of today you see these are the dominant errors, and they are somehow leveled out. Almost everybody has the same size. Just to mention how we calculated these finite size corrections, how we reduced the error from 2017 to 2020. The typical box was 6 Fermi, and it was too small because it meant a 2% correction. So we increased the 6 Fermi box to an 11 Fermi box and measured the difference between the AMUs on these two volumes. It turned out to be 18.1 with 2 statistical and 1.4 continuum error. But that's good because analytical calculations gave similar values between 15 and 17.8. And that meant that we can accept this one as a contribution due to the larger volume, and we can calculate using these analytical techniques the remaining contribution, namely A mu for infinitely large volumes minus A mu for the big volume, and the final result was more as precise as 0.1%. And here was our final result in 2020. And you remember the 693 of the white paper, and here we had 707 with a lot of graphs, 1.5 dozens of contributions. And if you have 1.5 dozens of contribution and you made your homework properly, that means your errors are trustworthy. That means that at least 2/3 of them should agree with the final result, and 1/3 of them should be out of the 1 sigma region. So let me come to the tail contribution, which I mentioned a couple of times. So we are speaking about the tail contribution, which is chosen to be larger than 2.8 Fermi. And here I show you this contribution of A mu for 2.8 Fermi to 3.5 Fermi. The lattice can be used. This is the lattice result. But at the same time, you can use the data-driven method to calculate the tail contribution. And the reason for that is at least twofold. First of all, as you see, independently which experiment you trust, the results are in perfect agreement. That's point one. Point two, that it's a tiny, tiny contribution to the total A mu. That means that even if we had a much larger error here, let's say a 5 times larger error than indicated here, it would be still no change on our final error. So even if you say that these experiments, which are in pretty good agreement, are not trustworthy and their errors are 5 times larger, yeah, and the final error is also 5 times larger, then you still have no change in the BMW 2024 data. So far, so good. I mentioned that as it is now, no other group, lattice group, has a full result for A mu. But there are very important partial results. And these partial results usually have the name of window observables. Let me explain the idea briefly. So here you have seen what we have seen already. That was our BMW 2017 result of this function, which we had to integrate. And the RBC UKQCD collaboration suggested that, okay, It's of course hard because here you have a lot of noise. Here you have a lot of cutoff effects at small distances. So we should multiply this function by a so-called window function. A window function between 0.4 Fermi and 1.0 Fermi. And if you multiply it, then you get this blue curve. And this blue curve has a lot of advantages compared to the red curve. It is far less challenging than the full AMU because the signal over noise ratio is far better. The lattice artifacts, the short distance artifacts and the large distance artifacts are much smaller. It has much smaller finite size effect because it extends up to 1 Fermi, so it obviously doesn't feel whether you have a 6 Fermi box or an 11 Fermi box. And a very important feature that you can calculate this quantity also using the R ratio technique. So you take these 4,500 something E plus E minus data, use a different kernel function than the one I used for the total contribution, and you can compare this calculation with the R ratio technique. All in all, it's about 2 orders of magnitude easier. So it's 2 orders of magnitude cheaper on the CPU side and 2 orders of magnitude easier on the manpower side. And in our 2020 paper, we have calculated this quantity. And here is the continuum extrapolation of this window quantity for various extrapolations. So there are improvements in lattice QCD, which help you to approach the continuum limit. And here you see various improvements, or you see here no improvements, but whatever you do, that's the result of this window quantity, something like 208. And if you use the R ratio technique, which is the data-driven method or the white paper technique, then you end up around 200. So it's already in 2020, we had a 3.7 tension, sigma tension for the window quantity. And as I mentioned, many lattice groups repeated these window calculations. The window can be between 0.4 and 1.0, but there are window calculations from 0.0 to 0.5, from 1.5 to 1.9, and everybody agrees with everybody. And that's a good news. Though there are no full lattice results available, only the 2 BMW results, but for these window observables, which is about 1/3 of the total AMU, there are results and they all agree. So here is the AMU between 0.4 and 1 for the leading order hadronic vacuum polarization light contribution. And as you see, everybody agrees with everybody, and it does not agree with the data-driven method. Here you have the total contribution. There are less groups who calculated that, but they all agree again. And as you see, the CMD3, which is the most recent E plus C minus experiment, agrees with this result, but the Babar and particularly the Colloy, they do not. So there is a huge tension between the BMW and the data-driven method. And if you take some average of these results, then the tension will be even more pronounced. As I said, it's not just 0.4 to 1, but there are other windows which were calculated by other groups, 0.0 to 0.5 and 1.5 to 1.9. And everybody agrees with everybody, but not with the data-driven method. And that brings me to my conclusion. Again, let me show my take-home message. It seems to me that we haven't found a discrepancy between theory and experiment for the magnetic moment of the muon. I was hoping for that. That was the reason I joined this direction of research, but it turned out to be, at least if we didn't make any mistake, that the standard model prediction and the experiment are in perfect agreement. But this perfect agreement is, of course, a highly non-trivial thing, because it's a success of the quantum field theory up to 11 digits. And don't forget that on the theory side, there are very different theories and techniques, and all of them are important enough, and we are sensitive to all of them. We are very much sensitive to the QED part because that's the largest part. And the QED is calculated by many loops, thousands of diagrams with a renormalization procedure there. The weak theory is a spontaneously broken field theory with a different way of renormalization, and it is also there in this calculation. And the QCD with the lattice formulation and obviously a non-perturbative renormalization is also an important part of this sum. These sum, the QED, the weak, and the QCD contributions, when summed, they agree with the experiment up to 11 digits, and I think it's an enormous success for quantum field theory. And that's where I have to stop, and I thank you very much for your attention.
Great. Thank you, Zoltán, for such a beautiful and clear lecture. Also very, very informative on a difficult topic like lattice QCD calculations. We open the talk for questions. Please go ahead and use the raise hand feature if you like to ask a question. Yes, Anthony, please go ahead.
Hi, thanks very much for the talk. Very interesting. I think I'm still left a bit confused about the role of the experiments here that we can see on this slide, B bar, Chloe, and so on. Is what you're saying that these experiments themselves are giving wrong results as compared to the, say, CMD3 experiment? Is it the experiments that have been giving wrong results and leading to this discrepancy?
As a theorist, of course, I cannot say that an experiment gives wrong result. But if you push me very hard, I think, and that's my suspicion, that these experiments, for instance, the Chloe experiment, probably had some unknown systematics, which either they didn't include or they underestimated the final error because of that. So the CMD3 experiment, that's in Novosibirsk, I think, and the community was scrutinizing the authors of the paper in a very, very detailed and almost aggressive way, and they didn't find any error there. So it seems to be that the CMD3 result is solid. And if it is solid, then we don't see any discrepancy between the data-driven method, because this is the result using the data-driven method, or the lattice, or the experimental value of the magnetic moment.
Okay.
Did I answer your question?
Yes, thank you. But is it fair to say that just looking at this graph, we can say that Chloe and CMD3 are clearly discrepant, and we can deduce effectively straight away from that there's an experimental problem, at least at the sort of 3 sigma level there. we don't even need to think about how it translates through to the comparison with the lattice gauge. They seem initially actually discrepant.
Absolutely, absolutely. Actually, if you just cut out the raw region, the raw mass region, so if it's from 600 to 900 MeV, yeah, then even Babar and Chloe have an about 3 sigma tension.
Hmm.
So the reason that you don't see these 3 sigma tension here is that there are other energy regions and the errors are increasing. But if you're just focusing on these 600 to 900, then the discrepancy was already there, 3 sigma. And if you include the CMD and look at the earlier averages, then it goes almost up to 5 sigma. So the method as it is dispersion relation or R ratio method is of course exact, but that needs good input data from E plus C minus. And if there is tension within the E plus C minus data, then of course the result is less trustworthy. But as I said, as a theorist, it's a slippery slope to criticize experiments.
Okay, thank you.
Thank you. Thank you. Thank you. Bernd, please go ahead.
It works. I'm a little bit confused by the different calculations, so maybe it's the orthogonal question to Anthony's question. So it looks a little bit that the calculations also change or are not in agreement with each other. Maybe I've mistaken this from your presentation. Is there any way, looking at the different experimental results and also at the different theoretical results, to find out which method is appropriate to calculate the muons G2?
I mean, the white paper method is the so-called R ratio method. I explained how it works. So you need the R ratios, you need a kernel function which is known analytically, and you integrate. So there's very little theoretical uncertainty in this technique. The only thing what you need is a precise data, the precise R ratio data.
Okay, and if this is not precise, you get
a wrong result.
Inaccurate result, or yeah. Okay.
And that's what the main difference between the CMD3 and, for instance, the Chloe data is, that around the rho peak, they differ quite a lot. So if you have the rho peak and the R ratio for the rho peak precisely or trustworthy or correctly or in a very good controlled way, then your result is good. If you don't have it, then it is less good. And these are, of course, far more difficult experiments than measuring the mass of the pion, because the mass of the pion we know to very high precision. And the lattice CD needs only the mass of the pion, the mass of the kaon, mass of the omega, and the fine structure constant, which we also know very precisely, and ds. Yeah? So in that sense, the input into the lattice is known with a much better accuracy than the technique needs it. Yeah?
Okay.
Here the input is known less accurately.
That's why. Okay. Thank you.
Did I?
Yes. Yeah. Now I understand. I also understand where's the source of the differences. But provided that in the future with better experiments we will have better values for the R values, you would probably also anticipate that the values will start to agree also with the lattice calculations?
I mean, if you have better values or similar values what the CMD3 has, yeah, then they agree with that.
Yeah, okay, you can see it here already. Okay, good. Thank you.
You're welcome.
Thank you.
And thank you for the nice talk.
More questions, please. Ashutosh, if you are there, I wanted your views on something. Are you there, Ashutosh?
Yes, yes,
Yeah,
I'm here.
nice to see you. Since you are an experimentalist in particle physics, could you share your thoughts right now, the situation with CLO, Babar, CMD3? Why are they disagreeing?
Again, like Zoltán says, I am an experimentalist, but not in this business. So I don't know how much out on a wing I should go, limb. Um, what I can tell, we are in grad school, you learn about the R, has huge implications. We all know from our coursework. So as a ratio of cross sections, the uncertainty, or what shall I say, a mistake in the experiment must be related to somehow the efficiency with which you have the denominator measurement, which is muons typically, and the efficiency with which you make the numerator measurement, which is all the hadrons. So one would have to look back at the papers. So I don't know the answer, but I can imagine how one would investigate. What were all the hadronic final states they were measuring? Which experimental components of the detector were involved, relative to which experimental components are involved for the muons, and is there exact cancellation in the efficiencies with which you measure the numerator and denominator? And it would seem, given the complicated final states, it's unlikely that there is exact cancellation, which means whichever part is not canceling in the ratio, experimental correction-wise, would have to be known confidently up to some level. Now, when these experiments were done, was it anticipated that they would be used as inputs to this extremely important quantity? Therefore, did they design the experiment with the anticipation that you would have to do this to a certain level of confidence? Or were the experimental goals something else? If they were something else, it's possible if you don't design for something that you can miss something. So in this sense, I understand CMD3 is looking for a particular 2-pion final state, which is designed to look very similar to the dimuon final state. So that seems like a specific attempt targeting this application, make the numerator measurement and the denominator measurement of R as similarly as you possibly can. Given the fact that the pion is not like a muon, but you try to measure them as similarly as you can. And so efficiencies and so on will cancel in the ratio. So to me, I mean, without reading the Chloe and the Babar papers, I can't say more. But there is something that says CMD3 thinking about this particular application has not measured the total hadronic final state, but has gone for the pi-pi, if I that fact correct. And when that attempt was made, we can see what has happened. Which gives me a feeling, again, just a feeling that one could go back at Chloe and Babar data and see if, rather than making total hadronic R, if they could emulate from their own data subset, which is specific, like pi-pi, for example, which may be statistically poorer, but systematically more robust. What would happen? Would they move towards CMD or what? Maybe it's an interesting action item what to think of.
Yeah, thank you. Thank you very much. That was valuable. Yes.
Yeah, thanks.
Thank you. More questions, please? Anthony, please go ahead.
Yeah, if I could ask another question. So going forward, assuming that, say, for example, the CMD3 results we can take as being the best results out of the experimental ones, and then there isn't an apparent discrepancy. So going forward, one is thinking about what this technique and your lattice field calculations and improved measurements of the actual G-2 might be able to tell us in the future. And I wondered, given the current accuracies, can you already put some sort of limit on the, so presumably a lower bound on the mass of some further particle, which we should be including in these calculations, but are not, something like that going forward?
Well, certainly. I mean, this paper in this 2020 G-2 paper collected in 3 years something like 1,000 citations. I don't know how many. I haven't checked it. But there is a huge interest, and people are using these results to answer questions what you are just telling me. And the reason that there are 1,000 citations is that people are calculating various things, and I'm obviously not knowledgeable about all those calculations. But when you have a 0.9 sigma discrepancy, then it can be that it is actually 0. And if it is 0, then you need something beyond the Planck scale to explain something which is so 0. You can use the accuracy and say that, well, within this accuracy, we can assume that it is within this band, and if it is at the edge of this band, what could be the mass? Yeah, you could certainly do that, and I assume that some people will carry out something like that.
I was just interested in, roughly where that might be, whether you're sort of at the edge of what the LHC can do, or whether it's much higher mass that is still possible.
What is known, that the electroweak contribution is 15.
Right.
And here we have perhaps a deviation of 10 or a little bit. So from edge to edge, so 198 to 208. So we have a tension of at most from edge to edge, something like 5. So that can give you an estimate that the electroweak theory gives you a contribution of 15, and what can give you a contribution of 5. Of course, it depends on the coupling, so not just the mass, it's a combination of the coupling and the mass, and you can certainly make some exclusion plot using that. That's what you mean.
Yeah.
Certainly you can do something like that, an exclusion plot on the coupling and mass plane.
Zoltán, could I push you a little further on this question?
Sure.
Is the electroweak contribution of 15, can we say it scales as some inverse power of mz?
Yeah.
Is it a quadratic power?
Oh, I would say so. Yeah.
Okay. So if I have to shrink the contribution by a factor of 3, all it takes is to double the mass. And so the limit would be 150 GeV. Anything above would be too small a contribution. So it's okay. So we are excluding up to 150 GeV maybe.
Yeah. So that was somehow the problem with these discrepancy of 25. Yeah. So the 25 was even larger than the electroweak contribution.
Yes.
So,
which would require pretty light.
Which would require something around the weak scale. And we don't see anything at the weak scale. Of course, you can always play around with the coupling. Yeah?
Yes.
So even your estimate is it depends on the coupling. Yeah, yeah, but you're right. If the coupling is similar, then it should be not too far away from the weak scale. Yeah. If we say that we are at the edge, and if we say that we are landing at the edge and the accuracy will be much better and the value around the edge remain the same, and we will see a discrepancy. So there are a lot of if in it.
Yeah.
That would be something like an outcome what you mentioned. But to be honest, I don't see that I can really contribute here further, because it was terribly difficult to cut the error by a factor of 2, and here I need an error reduction of a factor of 5 to see some discrepancy between the experiment and the lattice result, and then a factor of 5 is not possible from the experimental point of view. So there will be a factor of 2 reductions. If everything remains like that, then there is no hope in my lifetime to get it out with a factor of, so with a 5 sigma tangent. But as I say, this is just one result. Just read my last line. Yeah, other groups should confirm or refute. So it's an extremely complicated calculation, and everybody can make a mistake.
Thank you. Bernd?
Did I answer your
That's a
question, by the way?
Oh, yeah, sorry.
Did I answer your question, more or less?
That was Ashutosh, right?
Yeah.
Anthony's question.
Yeah. Okay.
All right, we go ahead.
Then I will add another question concerning your last sentence. Is there any interactions between the different groups, or is the codes for the computations, are they available online so that one can check each other's calculations? Is there or any kind of paper how to do the calculations between the different groups, so that there's a way to compare or exchange ideas? Or
Oh, absolutely, absolutely. I mean, even the paper in which we published these BMW 20 results, it's well over 100 pages, if I remember correctly. So
okay,
it's a very detailed paper.
very detailed with all.
The vanilla version of the code is available. If somebody asks me, then I can give the vanilla version. We don't give out the really fast version because we keep it for ourselves, but
I can't see why it is okay.
what's that?
Yeah.
So,
Answered my question. And
you-
I do understand, of course, yes.
You can cross-check some of the cheaper results, and then if it is the same, then you know that the same code was used. So then it's probably the
That's
same.
also the
Yeah.
non-vanilla version is still correct. Yes. Okay.
Yeah. I mean, the vanilla version and the non-vanilla version were cross-checked with each other. So
Okay, good.
they are the same. And there are a lot of communication between the groups, and as you have seen, so people are agreed on what to compare. Yeah. So here there are many groups comparing the same
Thank you.
same quantity. So we agreed on that. That's something everybody will calculate, and not 0.3 to 0.9, but this value will be somehow gold standard where we can compare the various groups. And that's very useful that we have the nice agreement.
Thank you.
Thank you. Zoltán, I want to bring up a somewhat more general point relating to the success of quantum field theory. I agree with everything which you said in the take-home message, but we are still worried that the theory, the standard model, as explained by QFT, has, say, 20 plus free dimensionless parameters. say the Yukawa couplings, for example. And one picture is that if we have to understand where these come from, we probably,
Absolutely.
sorry,
Absolutely.
yeah.
Absolutely.
Yeah. So one picture is that we have to go to the Planck scale or, beyond the current energies. I would like to contest that also based on some work that I have been doing. Namely, what is there to rule out the possibility that there is a theory more fundamental than quantum field theory, which is applicable at these very current energy scales, which agrees with the QFT results obtained so far, but which can explain the values of these dimensionless parameters. Would you rule this scenario out, the second scenario?
Absolutely not. I mean,
Okay.
there are, this is an aesthetic point of view, what you are saying. But even beyond the aesthetic point of view, there are still features of the standard model which tells us that the standard model is not complete. Yeah, we have the baryon asymmetry, we have the strong CP problem. So we do know that that standard model cannot be the final theory of our particle physics. And if you had a theory which explains these all 1.5 dozens of free parameters, that would be a great success. Absolutely.
Thank you.
Absolutely.
Yeah, I'll get in touch
The
with you.
idea here was, when I started this project, the motivation was that perhaps we find the energy scale, we find a scale where something new might pop up. And if this something new is somehow pinned down, then we can have a clue, as Ed Witten said, how to extend our standard model and eventually explain those 1.5 dozens of free
Yeah,
parameters.
so I would try to take a couple of minutes to convey where I'm coming from. This is from a relativist background. There is somewhat of a discord between relativists, say the Penrose school, and the particle physicists and HEP-TH physicists. Let's call it the Ed Witten school. What I am claiming is that even at these LHC kind of energies, in quantum field theory, if space-time is described using points which are labeled by real numbers, that is an approximation even at these energies. I don't have to go to the Planck scale. The reason classical space-time exists today is because the universe is dominated by classical bodies like stars and galaxies. Suppose I remove these classical bodies, I won't have a classical space-time, where I should still be able to do the quantum theory of microscopic systems. And that requires us to describe space-time without using real numbers, even at these energies. And lo and behold, that suggests that you get a theory which agrees with QFT at these energies, but comes with the additional bonus that it has a possibility of explaining these fundamental constants without appealing to the Planck scale or without going beyond. This is a message I'm trying to get across to particle physicists and quantum field theorists, but it's very hard to convince them. Yeah, anyway, I'm not asking you to comment back. I'm just telling you.
I mean, this is a very nice idea, and of course, I don't know the answer to that. Yeah,
Something has to give. I think on the one hand, while QFT is very successful, the standard model is very successful, I would also say that it is also in very bad shape because it has so many free parameters. And to think that the only way to explain these parameters is to appeal to Planck scale physics, I'm questioning that. Maybe we are missing something at this very energy scale.
Absolutely, it can be. Yeah.
Yeah, thank you. Thank you. Thank you for that. Yes. Yeah, I'm done. Any more comments or questions? I also want to thank you, Zoltán, for bearing with us and talking to us despite having a cold. So it's really nice of you to stay on. But I think if there are no more questions, we can also. Yeah, please go.
Hi. I'll say one quick thing coming back to Anthony's point. As Zoltán just said, the electroweak contribution is 15 on this units. So whatever discrepancy you take, 5 within errors or 35 as the Chloe Babar white paper number is, all those numbers, if you plug in with electroweak coupling, you get masses which are rather straightforwardly probed at the LHC, if not even LEP or Tevatron. Right? For a rather large discrepancy, if you invoke electroweak coupled particles, you would need a pretty light particle. So even Tevatron would have made it, LEP would have made it, LHC would make it easily. So what has been happening at the LHC now, to some level, is a shift to, as Zoltán was saying, fiddling with the coupling. So you're looking for something you could make because it's light, but you want a smaller correction than electroweak coupling. And one option is Higgs-like. So you invent additional scalars, which would not have electroweak coupling, but some mass-dependent coupling, the typical Higgs-like scalar, which could then perhaps induce an effect like this, but would be very difficult to spot at colliders. So that's one of the games being played, is to look for light scalars, which are experimentally hard to observe directly, just like the Higgs was hard, but somehow could make a discrepancy if there was a discrepancy. If the discrepancy itself goes away, then it's a moot point.
Yeah, absolutely. And that could eventually have to solve the baryogenesis problem too.
Yes,
So
that was the other angle, exactly.
Yeah.
Invoke light scalars for maybe explaining this, maybe also explaining baryogenesis, electroweak baryogenesis. So it was a nice idea, but maybe it goes away now.
yeah. But as I said, on my personal decision level, yeah, I am not the youngest person, and I see what the 0.9 sigma discrepancy means. Even the error on the green band will be cut by a factor of 2. Perhaps one can cut the pink band also a factor of 2. It's not going to be a 5 sigma effect.
Yes.
That is true. Yes.
That's a good point, actually. That's a good point. Yes. Yeah.
So it was a lot of work, but the outcome is not that what we hoped for. Yeah.
Yeah, that's where I feel that instead of pushing the experiment in the hope that we will find a disagreement with the QFT-based standard model, my personal opinion is that theorists need to work harder how to explain the symmetries of the standard model, why SU3 cross SU2 cross U1, why 3 fermion generations, why these couplings. These answers to these questions to me, to my understanding, point a shortcoming in the theory at these very energy scales. It's too much, in my view, to expect that one day the Planck scale theory will fix everything, and then all these questions will get answered at low energy because we know the high energy theory. In a way, saying that gravity, in some sense, is important for QFT and the standard model, even at these energies and not just at the Planck scale, where gravity has 2 aspects. One is the strength of the gravitational field. That becomes important only at the Planck scale. But gravity has another aspect, the point structure of space-time, which is not a feature of the other interactions. The point structure of space-time is a part of a larger view of gravity, And we should be, Einstein questioned that. I mean, the so-called Einstein whole argument, but then it was too much before his times. So, and this I feel is a discord between relativists and particle physicists. Relativists like Penrose know this quite well. Penrose just told me that, yeah, you have a good point, but I don't know what to do about it. So,
Yeah. Yeah. Okay.
Tejinder, in support, I would add that we experimentalists, lacking any other guidance from an alternate perspective, are constantly being driven by, I guess you could say, QFT, standard model, to keep building bigger, bigger, bigger.
Yeah, that I agree.
That's
But I
pushing the
think,
limits of funding and not technology, I would say, but funding.
yeah, but the goal seems to be to find a discrepancy with the standard model. I'm saying the goal could be different. Like if some theorists are saying the Higgs is composite, like the talk we heard previously from Kaustubh. Yeah, so those kind of questions, in my view, need greater merit. And I would add to that in the same list the question of dark matter. I mean, everybody seems to believe in dark matter as opposed to Milgrom's modified gravity, modified Newtonian dynamics. I find it very painful how less attention Mond gets, but whereas there is no evidence for dark matter.
Absolutely. Absolutely.
For
We should
particle.
be open. We should be open for alternative explanations. Absolutely.
Yeah,
Absolutely.
thank you. Yeah. So questions like this, Ashutosh, I was thinking, should drive experiments. But they need support from theory. They need support from theory. Theory seems to be going along very conventional lines. And in my view, that is why it is stuck. Yeah. Bernd,
So Sundar, I
go
would
ahead.
say that with support from theory, what we want are alternate predictions.
Yes.
Without
Yes.
that, we can't motivate an experiment. That's the
Yeah.
culture of the field.
I agree. The predictions should also be sharp. They should be not just a statement like there's a second Higgs. I have to say more. Yes, I agree.
You go
Alternative,
out on, exactly. You go out on a limb, then the experimentalists will also go out on a limb.
I agree. Yeah. Have a different theory which explains everything that QFT does, but makes a prediction which disagrees, which you all can measure.
Yes.
Hmm.
That's
Yeah.
sort of a condition for getting the experiment built.
Yes.
Many a time, not necessarily every time, but often.
This is also the gold standard in the history of science if an old theory is replaced by a new theory. Explain the success of the old theory and predict something new. These are the 2 points you have to have for a new theory to take over an old theory. And the Einstein whole argument was maybe not too early. I mean, already at the beginning of quantum theory, so next year, 100 years ago, people speculated that the space-time coordinates of the electromagnetic field should not be described by real numbers, but by matrices, so by non-commuting variables. So this is very...
By electromagnetic field, you mean the quantized electromagnetic field?
Yes.
Yes. That's very interesting. Who was that? Born and
Jordan, the first paper on quantum mechanics.
Yeah, but that message has been lost, right?
It had completely... Okay, it was only in a footnote. Maybe that was the problem. So it got lost.
Sorry, could you say which paper? Born and who?
Born and Jordan. So it was the German for Quantenmechanik 1. The English version should be on Quantum Mechanics 1.
I think this is the foundational paper.
The foundational paper, the very first paper.
Born and Jordan, 1925.
1925.
Okay,
thank you. Quantenmechanik. Zeitschrift für Physik, so Physical Journal of the German Physical Society at that time. I think it's now the European Journal of Physics. I don't know. One letter, I forgot about the letter for the, I think it's H or G now. So, but there should also be an English translation. So the original German version is also available on the internet. And there's one chapter where they describe the first step on the quantization of the electromagnetic field, where they say the field strength should be described by non-commuting operators. And then there's a footnote. At the moment, we still use space-time coordinates for the field operators, but maybe the space-time coordinates should be replaced by matrices.
I think that's a consequence of the Einstein whole argument, that if you quantize, say, the gravitational field, you cannot keep the underlying space-time coordinates as commuting real numbers. Quantization of the overlying gravitational field already implies that your space-time manifold has also become non-commuting.
That's true.
And this statement is independent of the energy scale. I can, in principle, quantize gravity at the electroweak scale. It would be a very, very weak quantization, but that would already imply that space-time cannot exist even in low energy quantum gravity.
Yeah, you can still have a non-commutative space-time which is flat, for example, and then
Yeah,
later a curved
yeah.
one.
But if you try to do particle physics on a non-commuting flat space-time, is every likelihood you will
Be
not,
forced to introduce something like gravity.
and you may be able to explain these couplings. These couplings are then driven by the non-commutative structure of the space-time.
This, by the way, was the hope of David Finkelstein, who also worked on quantized space-time. This is exactly what he wanted to accomplish. So by quantizing space-time, deriving all the coupling constants, he said we're still stuck in a classical picture, and that's why we have so many free parameters.
Yeah, that's my view too. I mean, what is important is that we somehow start this dialogue with particle physicists, that please, we relativists have something useful to say about particle physics at electroweak energies and not just at the Planck scale.
I also agree that it's a bad idea to put all the open questions to the Planck scale, which is a little bit inaccessible. So it's like pushing everything under the Planck scale work, so to speak.
That's why it's good that in this series, we at least now have particle physicists joining us. Zoltán came today, Ashutosh comes, Kaustuv Agashe was there. And maybe we increase this dialogue between quantum foundations and particle physics. Okay, great. Thank you. Thank you all. Should we call it a day or anything more? Yeah, I think we should be moving ahead now. So
by the way, who will give the next lecture?
Thank you very much for the invitation.
Thank you. You're most welcome. The next lecture is on October 4th by Juelich, ETH Zurich. He will talk on a theory of quantum jumps.